feel like I was talking like Gollum. It hears me, does it? You know, or something like that. Okay. So there's one more paper that I want to talk about. So when we get to neurons, we're really at the end of at least chemical evolution. You know, oxygen is at 20% of the air. It can't get much higher, or else the world's going to literally like ignite, you know. So oxygen is going to stay down. We're not going to have any further oxidation of the environment. Let's circle back around to a topic from chapter 2, though, because now that we've covered kinetics, we can go back to one of the fundamental messages. Different elements have different stickinesses, and this causes them to work, and this also causes them to work differently in different organisms. So Pepto-Bismol is an example we're going to come back to. The pink color is literally from the bismuth element. So there's this, and this is actually a pretty complex paper too. It's a systems paper, which means that they're somehow looking at the entire organism, and they're looking at a lot of different possibilities rather than just one possibility, however they do it. So I'll talk a little bit about how they do it. And this doesn't appear to be how Pepto-Bismol works at first, but it does have a deep connection because it's about how human cells dispose of bismuth in a sort of self-propelled kind of way. So this happens automatically that human cells can get rid of bismuth. And also what's involved is another molecule that was mentioned way back in chapter 2, glutathione, which contains sulfur. So we're talking about sulfur and bismuth working together, and somehow this has to do with how Pepto-Bismol works. And the basic thing about Pepto-Bismol, when do you take Pepto-Bismol? Yeah, so when you have like, and what it does is it will kill bacteria in the gut, and it will pass on through, you know. I don't know what level of toxicity bismuth is, but it doesn't matter that much if you're just drinking it because it will pass through before it ever does anything to you. The thing is, if you were submerged in Pepto-Bismol like a bacteria is submerged in it, it would probably do a number on you too. But because bacteria are so much smaller than you, the Pepto-Bismol is able to attack them more than you. So what is the basis of this difference? Is it just size, or is there something more specific going on? And it's also related to, why is it that Pepto-Bismol doesn't bother my stomach cells as much as it bothers the bacteria cells? So they were, this is a figure from the intro article to this. It shows glutathione, which is the most useful thing that I think is up there. And remember that the active element in glutathione is sulfur. So we're talking about two parts of the periodic table interacting. Now, because this sulfur is sticky, it floats around the cytoplasm, and it can bind all sorts of sticky metals. So look around and see the different metals that you see interacting with glutathione in some way. These are all metals that get into your cells. How do your cells get rid of these nasty metals? Okay? Gold gets in. Glutathione is involved in getting rid of the gold. Whenever you see G, a GS especially, that's glutathione. The S is for the sulfur. It shows us that the sulfur is what's crucial here. When copper gets into the cell, glutathione's involved in getting it out. When arsenic's involved in the cell, glutathione's involved in getting it out. Again, sticky sulfur, sticky metal. It's sort of a sacrificial kind of flypaper type of molecule. And then finally, in blue over here, bismuth gets into the cell, and this paper established glutathione is also responsible for getting it out. It's a really good multi-purpose kind of a molecule. And it's kind of cool that we can have a defense shield against so many different parts of the periodic table based on just sulfur. Now, the sulfur is doing different things. You have different proteins, different ways they get in, different ways they get out. But the basic thing is that glutathione's at the core of all of it. The one thing that I want to see is I want to follow this. Bismuth gets in. Oh, and by the way, you can look up and down. You see two things at least here that are unusual. Bismuth 3+ and arsenic 3+. You can see right away those are sticky ions because they have 3 charges where the other ones have 2. Gold happens to be sticky even in its 1+ state, and copper, as you know, is super sticky even in a 2+ state. So fundamental chemistry is what's going on here. What happens to the bismuth? So the bismuth binds glutathione, And then it can be, there's a protein called MRP that's able to move it out. And it can either completely throw it out, or it can throw it into a vesicle. And when it's in the vesicle, it's not bothering anything, so it's like throwing it into a closet until, a later day, and, the cell can forget about it. If you remember about arsenic, actually, the cell does this with arsenic too. It's one of the reasons why it's one of the reasons why that researcher was fooled in the first place, because there was arsenic inside the cells, but it was in the cells in vesicles inside the cells, not in the cells in DNA bonds actively making life. So when you look at this is the paper itself, and this shows you 3 different pathways that your cells can do to get rid of bismuth. You have, and I thought I had animations, but I have them right here. They basically took bismuth and they threw it at cells, and they saw what would happen. I want to show you the actual words they use so that you can get used to this, and maybe when I ask you a question, you'll be able to translate those words, okay? So they tested bismuth uptake in human cells, and they found a biphasic pattern of saturation and exponential growth. In other words, they saw at least 2 things were going on, because I had at least 2 rate constants, or less likely, a second order rate reaction. Most likely, remember how we talked about pharmacokinetics, most reactions actually end up being first order, even if they're complex. So they saw something complex, and they said to themselves, that's probably a complexity in the number of steps, not in there being a complex step. So they saw that the cells took up bismuth, bless you, not with a single exponential, but with 2 exponentials at the very least. And so they modeled, and they said, okay, is this active or passive? They found that a simple passive model accounted for the behavior nicely. And the passive model could be just, passive means that it's not getting through a protein actively. The most likely passive form is it's just pushing its way through the membrane. So it gets through the membrane, and that depends on the membrane surface area, okay? It also means that smaller cells have higher permeability, because the smaller you are, the smaller volume you have, the bigger is your relative surface area. If you're this big, you have more surface area, but it's gone up by less. Relatively speaking, you have less relative surface area relative to your volume than if you're this big, because you have all this surface area to volume ratio. That's the fundamental mathematical thing. That's actually also related to calculus, if I think about it way back. If you think about the equations for volume versus surface area, you can prove that this is so if you doubt me. Go ahead and doubt me. Just prove it, okay? But they also found that there's at least 2 things going on, which they eventually resulted in seeing that there are 3 ways that the cells can be protected from bismuth. There's the cell membrane itself, which is way number 1. It's hard to get across the membrane. And then there's 2 ways that the cell is actually, once it gets inside, the glutathione is actually consumed 2 ways. And this is they found 3 possibilities for the biphasic kinetics that they see here. So that's point number 1 I want to show you. I want to show you the biphasic kinetics. And then when they're talking about passive transport, they're talking about the kinetic constant for the transport is proportional to the surface area. In fact, it's proportional to the surface area to volume ratio. And I just want you don't have to recreate this, but I do want you to read it. Look up here, you should see something familiar. Sometimes they use different symbols, but you've got to, if you look carefully at this, they're using different symbols for the same things we've talked about. The permeability is P, it's a proportionality constant. You multiply it by the surface area of the cell, and then you have the concentration difference. They use C and Cb for the extracellular and intracellular concentrations of the bismuth. But that's really a C initial and C final. Okay? So, and the biggest thing you see right here, which chapter does this remind you of? We started talking about D, they even use J, I think, the same way Atkins does. So the change in concentration of whatever is what he showed by J, and the dJt dt is this. And so this is a basic kinetic equation, If we integrate this, we get an integrated rate law. This is related to a rate law. It's just using, and by the way, we used V for this symbol many times. We could substitute V, and it just shows us that the rate constant is related to two other constants, the surface area and the permeability, which is really, I would put the permeability as being most like a rate constant. But, you know, a lot of times we will say that one constant is a result of two other constants because you can do an experiment to say what those two constants are. Okay. So the amount of solute at time t is the product of the intracellular concentrations of solute in the volume of the cell. In other words, they did the integral of this. You see you're going from djt to jt, and you end up saying, oh, it's Cb at time t times the volume. And so they found a relationship to the surface area here, the volume there, and they did this. They solved equations S1 and S2 together. This is like a PChem problem. You know, someone should tell Atkins as he's getting ready for the 3rd edition. He can put this in there. Because you see what you see. You see e to the negative constant times t. It's hard to see this constant, but I'll tell you, their surface area over volume is a ratio of that constant. In our experience, we say that's the rate constant. So their real addition here is to say the rate constant depends on these fundamental physical characteristics of the cell. It depends on the surface area, A, and it depends on the volume, V. And then it also depends on the permeability, which is where they throw everything else, honestly. But they can show that the constant, the rate constant K, is made up of 3 other constants, 2 of which we can calculate just by measuring how big the cell is. Okay? So I just want to point out that this format, when you see this, you remember the P. We measured the dP dt, and this should look like the product part of our Chapter 7 equations. Go back and check me out to confirm that I'm right. But they ended up seeing that the math all works, and if I have a bigger cell, then it will change in a predictable way. I can plug that into the equation. I can predict how fast the bismuth will get in. Here's another figure that they had for it. And I just want to show you this because there's our friend the hyperbola, okay? This is a hyperbola for time versus intracellular level for the bismuth getting into the cell. And they had a mathematical model that would predict what the shape of this curve would be. And it ends up being able to predict what will happen when you have a bigger cell, a cell with more volume, a cell with more surface area. Because it depends on surface area and volume, then you can make a very simple situation. Here's a non-physiologically realistic model of a cell, okay? But this shows you, this has a certain volume. These two have the same volumes. Which one has more surface area? The second one. You know, you have a ton more surface area when you have the volume broken up into smaller chunks. And this is their argument that surface area is just inherently higher for a small little bacterium than it is for a big human cell. And because the permeability of the bismuth depends so much on just getting through that barrier, that by itself means that bismuth will kill bacteria a lot faster. It'll get into the bacteria and it'll kill them a lot faster than our cells will. Even despite that, we also have the 2 glutathione-based ways of getting rid of it. So, and that helps too. And that's why we don't need to be worried about drinking Pepto-Bismol. It is toxic, but we can deal with it. You know, and our cells are even inherently able to deal with it, you know. So predict from this, you know, would it be okay to give Pepto-Bismol to your dog or not based on this? What would you say? Your dog, like another mammal, about the same size, cells about the same size as you. Now, I'm not a vet. I'm not making a recommendation. But what would it be reasonable to say? Would it be reasonable to say yes or no, do you think? Yeah, it's probably the same because all of these characteristics, cell size, surface area, and if permeability really is the main thing going on here, the dogs probably even have glutathione defense systems like we do. I still wouldn't do it without talking to my vet. Don't worry. You know, I'm not going to give Pepto-Bismol to my dog. But if I saw a paper saying that it was okay, this would make sense, okay? So, now it's your turn. These are the details about the presentation itself. I want you to pick an element. I want you to give a 10-minute presentation. It's going to be on 531 with the one exception of Angelina. I want you, as you're doing it, after you pick your element, start with the index. I bought a special computer program to make that index, so let's put it to good use, okay? And you can find all the places where that element is mentioned. And I want you to mention how it is used. Make sure that you talk about at least some geological uses of it, chemical uses, and biological uses. Use its chemical personality. We had data talks 7 through 9 that we showed those right after the lineup picture. You can look up your element from there. You can talk about how it goes through, and I want you to pick 2 peer-reviewed original research papers that say something. You won't be able to go into any kind of detail, but if these papers have some kind of chemistry in them, some kind of structure, some kind of dependence on the chemical personality is what you're really looking for, then you're good. You know, I want you to be able to have a very open-ended kind of research project here. So remember how the data talks, with the data talks, basically, I just gave 2 examples of a lot more time to go into more detail, but in each of those I showed you how the PChem topics related to these. If you see something from chapter 5 or chapter 4 or something like that, that's the kind of connection I want you to make. Now I'll pick up on that whether you show it or not, you know, but if you highlight it, it will help all of us, and it will be a form of studying, because you see that thing. I just showed you that P equation. That's a little bit form of studying, you know. You still have to study, right? But this can actually all feed together if you make it do so, okay? Tell us about how it's used now. Tell us about how chemists might be able to use it in the future. That's a topic that you can talk about. Or you can find a geology paper that talks about how it's used, you know, even historical uses. Basically, how is it used? Talk like a chemist, think like a chemist, and show us how the chemical personality plays out in real life. With that in mind, I know we've already talked about some of them, but I said that there's a bunch that you can choose from, and I made a list of everything that I think would give you a good presentation, a good thing for it. So, oh, I'm still recording, so I'm going to go ahead and turn that off now.